Here's an integral that's useful in some applications in electrical engineering and signal processing. The function sine x over x is also called the sinc function, S-I-N-C, and it comes up in Fourier transforms and stuff. And sometimes we need the integral of it. If we try U substitution, integration by parts, trig substitution, triggered entities, all of that fails. You might say, oh, let's try Wolfram Alpha. Wolfram Alpha knows everything. If you try that, it just says, oh, this is something I recognize called the sine integral. And that's all it says. It's like, okay, this is a famous hard problem that has a name, and here's the name of it, but it doesn't actually give us a formula. So what are we going to do if we need an approximation of this, for example? Well, let's try power series. So what is sine x? Just by itself without the dividing by x. We know that's x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus dot dot dot. That's just sine x. Now let's divide by x. And that'll give us a power series that is sine x over x. So if I divide x by 1, if I divide x by x, I get 1. What if I divide x cubed over 3 factorial by x? It's going to take a power off the cubed, right? So I'll get x squared over 3 factorial, because x cubed over x is x squared. X to the 5th over x is x to the 4th over 5 factorial minus x to the 6th over 7 factorial plus dot dot dot. So that's just a power series for the integrand. And then let's actually do the integral. What do you get if you integrate 1? You get x. If you integrate x squared over 3 factorial, let's copy the 3 factorial, integrate x squared, you get 1/3 x cubed. We'll copy the 1 over 5 factorial, and x to the 4th when you integrate gives you 1 over 5 x to the 5th, 1 over 7 factorial, 1/7 x to the 7th, plus dot dot dot. Is that anything we recognize? Well, it sure feels like sine. It's got odd powers and everything. It's got alternating signs, but it has an extra factor of 1/3 and 1/5 and so forth. It'd be good to write a general term, so let's do that. You might guess it's something times x to the n. That would kind of make sense, but that will give you both the even and the odd powers. If you just let n be any integer, that's sometimes even, sometimes odd. So let's say, nope, that gives both even and odd powers. So we need to be thinking about, how do I get just the odd powers? Let's try the integral, the sum, n equals 0 to infinity. I mean, we kind of say that anyway, right? How about x to the 2n plus 1? That's going to give us odd powers, divided by 2n plus 1 factorial, 2n plus 1. So this way, like if we have 5 for 2n plus 1, we'll have x to the 5 over 5 factorial times 5. That's looking good. And then we need the alternating signs, so we'll throw a -1 to the n there. And then we'll think about whether that gives us the right signs or not. So let's think about that. At n equals 0, we get -1 to the 0, which is +1. Let's check what term that is. We have a +1 times x to the 2 times 0 plus 1 over 1 factorial times 1. Altogether, that's x to the 1 times +1. So it's +1 times x. At n equals 1, we're getting -1 to the 1, which is -1. So we have -1 times x to the 2 times 1 plus 1 over 3 factorial times 3, which overall has a negative sign on it. And we got 1 over 3 factorial times 3 x to the 3. So that's working out okay. So it seems like our first guess there actually ended up working. If we wanted to start at n equals 1 instead of n equals 0, I'm not sure why you'd want to do that, but you could just change all the 2n plus 1s to 2n minus 1s and switch the power to n minus 1. All right. Let's take a look at our result on Desmos. Here I've got f of x equals sin x over x, that's the sinc function, and I'm integrating from 0 to my upper limit here, which I can move, and the purple curve is going to trace out the cumulative area so far. So we're adding boxes of positive height, so our cumulative area so far is going up, but it's going up a little less quickly here when the boxes aren't quite as tall. And then when I move over here, now my boxes have a negative height, so my cumulative area so far is going down, and then it goes back up again when f of x is positive again. So, and it goes up and down a little bit less each time because sin x over x has a smaller amplitude as time goes on. So we're getting that curve over there. On the negative side, we're adding up boxes of positive height but with negative width, so our cumulative area so far curve is decreasing as I go backwards, or you could say it's increasing as I go forwards because I have positive height boxes, and then I'm adding up negative values, so it's getting back, the cumulative area is getting back toward the x-axis. So we see that same kind of wiggly behavior, but with the wiggles being less and less each time. So that's just adding up box heights. That's not taking the actual antiderivative. Let's go take a look at that sheet. So here I have sin x over x, and I have the power series that we got. Notice writing the general term allowed us to type it in as a sum in Desmos rather than having to type in the first term and the second term and the third term. Here I can go all the way up to 100 if I want, and I get this nice curve which kind of mimics what we saw on the other sheet. I can even tell Desmos to take the derivative of this with capital F prime, and hopefully that will overlap the original curve, the red curve. We'll see in just a sec here. Yep, that looks good. There's something more interesting to explore here. Let me zoom out on this axis, and I'm zooming out, and it just stops reporting any values right there, which is kind of interesting. What would you say that is? Like 33-ish, 34-ish? So can we explain why that might be happening? So let's type a quick note there. Why is it not reporting any values past x equals 34-ish? Well, the maximum value that Desmos or even most math software can represent is about 10 to the 308th. It's a little bit larger than that, but I mean that's all you need to remember, and that's in Desmos, Excel, MATLAB, Python, R, even C++, Fortran. I haven't used Julia, but I'm guessing Julia would do that. It's called IEEE double precision. And apparently when I'm using powers like, we're using like 34 to the 2 times 100 plus 1, and that's getting awful darn close to 10 to the 308th. So after that, it just starts overflowing and saying, oh, this is basically infinity, and then saying, well, I can't plot that. So that's something to be careful of with really high power polynomials. You can end up with fantastically large numbers, even though you aren't really all that far away from 0. So just a bit of numerical wisdom for you there. So then this brings up the question of how do I know when to stop plotting? How do I know when to stop adding terms? Well, this is an alternating series, so we can use bounds from the alternating series test ideas. I forgot to show this is actually an alternating series because I do have a -1 to the n, just like I had with my paper and pencil work. It's just that I hadn't made that column wide enough to see it.